Auzu billahi minesh-shaytanir-rajim. Bismillahir-rahmanir-rahim. This is our lecture number 27. In previous lecture number 26, we have discussed about the Rayleigh wave equation, that we have derived the Rayleigh wave equation, and from that equation, which is here equation number 1, that we can have speed of Rayleigh wave with the help of this equation. And you can see that where we have talked that RC phase speed is independent of the wave number k, and we were saying that if speed is independent of the wave number k, then that wave is called non-dispersive. So the Rayleigh wave is non-dispersive wave because c is independent of the wave number k. So in today's lecture we will see the existence of solution of this equation for the speed of Rayleigh wave in this domain, that when c lies between 0 and ct, we will see that solution of this equation of 1 exists in this domain when c lies between 0 and ct. What is ct? Ct is the velocity of transverse wave. So it means that we will have to show that speed of Rayleigh wave lies between 0 and speed of transverse wave. So let's see that how we can do this and how we will show that our Rayleigh wave speed, which will be denoted by c subscript capital R, Cr, lies between 0 and ct. So we can simply see that, let us suppose that our left hand side of equation number 1 is f of c, that this is some function of c, as c is variable here only, and ct and cl, they are the constants, and they are coming from the material which will be used to fill the half space will give us the values of these cl and ct. And these values of cl and ct, these are constants values and are given in the literature for different types of material. That if you have aluminium isotopic, steel isotopic material, whatever isotopic material you will use, you must have the known constant values of these cl and ct for that particular material, which you can use in this equation number 1. Because you know that the cl and ct, they depend on the Lamb's constant lambda and mu and density rho. So it means that if you have material, then you have the density of that material, and also you have the Lamb's constant lambda and mu, and the lambda and mu are also given in terms of C's. What C's means? C11, C12, C13, components of elasticity matrix for isotropic material. So these are the known things. So we have only one variable, which is c, which is basically value of c from this equation number 1 will be the Rayleigh wave speed. So let's see, when we put this left point of the interval here, then we have, you can see that we have 0, 4 minus 4. When c is 0, f of 0 is equal to 0. So when we have, let's put c subscript capital T instead of this c, we will have this term 0, and this will be minus 1. 2 minus 1 whole square minus 1. So it will be f of ct minus 1. Then you can see that on the left hand point we have 0, and on the right hand point we have minus 1. So this will be in this form, something like this: 0 0, and ct and c is here somewhere. And we have seen that at 0 we have 0, f of 0 is equal to 0, and for f of ct we have this, that value of this f of ct is minus 1. So graph will be here, the graph will be will be like this. If it will go like this, then it can be moved like this, and end will be here. It can go from here, then there, and here. Now we will see that either graph is increasing at this, that our function is increasing at this point or decreasing at this point. Now we will see with the help of second derivative test. Let's see. No, this is the derivative f dash c. Then you can see that if you will put c is equal to 0, then derivative will be 0, the slope will be 0 at 0. This is f dash c. This is simple, the derivative. Then you can do this by yourself. This is simple calculation, and this thing does not exist. You can ignore this. When you will use c is equal to 0, it means 0 0 and 0. So f dash at 0 is equal to 0. The slope is 0 at 0. No, we will calculate the second derivative. When you will calculate second derivative, then it will be like this whole things, this and this. No, you will use c is equal to 0 for second derivative. Now when you will use c is equal to 0, then you have this simple form. Again, if you will simplify this, and you will have this. You can write this, and you know that your longitudinal wave speed is greater than the transverse wave speed, and then when you will take the reciprocal, then you will have this inequality in reverse order. So it means that this thing will be positive. This thing will be positive. And this thing will be positive, it means that f double dash 0 is greater than 0. So it means that we have relative minimum at this point. When we have relative minimum at this point, it means that our function f is increasing at c is equal to 0. If you go on right side of 0, then you can see that our function will be increasing at this point, that the function will be at greater than 0. So that at that point the function graph is like that, concave up at that point. This is the second derivative that you can see this, or you can study, or you can revise this second derivative or first derivative just from your calculus of FSC or whatever you can use to revise this. So function is increasing at this point. So we have these things. At 0 function is 0, at ct function is negative, and also at 0 function is increasing. So graph will be like this. It will go like this, then it must cross this line to come at this position. At least one time it must cross this line, this x-axis, this horizontal axis, because we know that function is negative at this point. So to achieve that negative value, your function must cross this axis at least one time. So we have at least one root of Rayleigh wave equation in this domain. 0, this is inequality, inequality, and this is c. Do not mix this c with this symbol and this symbol. You can read it as C is less than Ct and this C is greater than 0. So we denote this relative speed by Cr, as I have said in the starting that we will denote our relative speed with C subscript capital R. Now we have seen that our root of this equation lies in this domain. So we move something further about the existence of the relative speed. Let's see what happens if we will take the half value of Ct, that what is the value of function at this Ct by 2 at this point. Let's see what happens. If you will use Ct by 2 at C in the function f of C, then you will have this. On left hand side you have f of Ct by 2 and on right hand side you have this. Simplify this a little bit, you have this and you have this. Here we will use this Greek letter kappa. So this is the standard notation for the ratio of Cl to the Ct, that this is the material constant. That if you will use the word material constant kappa, then everyone knows that kappa is equals to Cl by Ct. So we will use it here. So our function, when we will use C equals to Ct by 2, will in this form. So this is positive if this is positive. We have written this thing, nothing else we have written. We have just written that this is positive when this is positive. You can write this as, simplify this like this, then you will this. At the end you will have this kappa square greater than 1.2913. It means that you can write this kappa square is greater than 1.3. Now let's see whether this thing hold or not. It will depend on the range of this kappa, this material constant. We know that, I know that, you know that. So it means that we know that kappa square is this. Kappa square in terms of the Poisson ratio of the material is this. No, you know that. We know that the kappa is Cl by Ct. So no, it is your homework to convert that form into this form. That kappa is Cl by Ct. So use whatever you know and whatever you have to know, and with the help of that information you have to obtain this relation for kappa square. So it is your homework to obtain this relation. No, this is something else. This is your homework. No, let's come to the point. No, we know that this nu is Poisson ratio, and I have already told you that Poisson ratio is the ratio between the contraction and expansion of the material. That and it has different values for different type of materials. Theoretically, it has minus 1 by 2 to plus 1 by 2 value. And if I am not wrong, but practically I am sure that its value is 0 to 1 by 2. Practically means that most of the materials, most of the metals has the value between 0 and 1 by 2 for this Poisson ratio. Nu, value of nu is 0 to 1 by 2. I will confirm this thing in the next lecture. The value of this nu varies from minus 1 by 2 to 1 by 2 in general, and for practical purpose we have 0 to nu. So we will Now to find the range of this kappa, we will use the value of nu between 0 to 1 by 2. Because practically we have this type of range for Poisson ratio lies between 0 and 1 by 2, that for different metals, for most of the metals we have between 0 and 1 by 2. So if nu is 0, then you have 2. It means that our kappa square is greater than or equal to 2. And when you will move towards 1 by 2, your kappa square will go on increasing. And when you will have 1 by 2 exactly, then kappa square is undefined. You can see that 1 minus 1, 0. It will be undefined. So range of kappa square will start from square root of 2. That kappa square is greater than or equal to 2. But our calculation is telling that our kappa square is greater than 1 by 1.3. So it means that this relation is covering the whole domain of kappa. Suppose if instead of this 1.2913, which is 1.3, if we have 3 here, that we have done all this calculation, and at the end we have kappa square greater than 3. If it happens like this, kappa square greater than 3, if it were kappa square greater than 3, then we were wrong. Because if kappa square is greater than 3, then this thing is telling that this supposition is missing some domain of kappa, because our kappa is satisfying that kappa square must be greater than or equal to 2 in general. So if it is here kappa square is greater than 3, then it must be wrong, that we are missing between 2 to 3. So as this is covering the whole domain of kappa square, so this thing is wrong. Hence it means that this is right. It should be Ct by 2, not 1 by 2 Ct. It will be f of Ct by 2. Please crack this thing. Now it is also your duty to listen the lecture very carefully, and if there is some mistake, human error, then you must tell me that, sir, you have done this thing and it can't be like this, it would be like this. So it will be f of Ct by 2, half of Ct. So we can write this thing, this is less than 0, this is on this is positive. So Cr can be lies between this range, and for different values of nu we have this thing. If you will divide Cr by this Ct, then you have 1 by 2 less than Cr by Ct less than 1. That for 0 we have this value, with this we have this, for this we have this. That means that when we have 0.5, then we have 0.955. So you can see that our C by Ct lies between 0.5 and 1 by 2 and 1. You can see that. Now there is a good approximation. This is the formula, approximate formula to find the value of Cr. I am writing this directly. I didn't derive this. So this is the formula. By changing the value of nu, you can have different value of Cr. Obviously you need Ct, value of the transverse wave. It means that if you have material, then you must have nu, then you must have Cl, you must have Ct. Use that Ct and nu to find the relevant speed for that particular material. So this is the value of Cr is unique for one material, that which material you will use, you will have one value of Cr. No, you people have to show this, and this would be your assignment. I will give you that, show that the value, this is unique. How will you show that? When we will study the isotropic material and its dispersion relation, then we will form the spectrum of that, in which has the Lamb spectrum curves. That curves Lamb modes would be there. Then you will see that only one mode will approach this CR. From there we will see that the value of CR is unique, and you will show that there is only one mode which approach that CR. Oh, thank you so much.